Like I said, today's lesson is about correlation. What we're going to do is we are going to test whether relationship between two variables exist, and then at the same time, we will find out whether such relationship that exists or correlation that exists between variable is significant or not significant. We will know the strength of the association or as the correlation goes between variables, and at the same time we would like to find out whether such relationship that exists between variable is significant or not. Okay, exactly, we're going to talk about this morning about the Pearson product moment correlation. We have the Pearson product. So we have this so-called the Pearson moment product correlation, also known as we have the Pearson R, or the Pearson's coefficient. So with the Pearson's R, what we will do about the Pearson's R is that this is a test of association. Now, other tests of association, as far as I know, there is also chi-square. Chi-square is used also to test whether association exists between variable. But in this case, chi-square statistics is intended for categorical data versus numerical data. So your two variables must consist of categorical and at the same time numerical data. But for Pearson's R, both variables are or must be categorical. I mean, must be numerical in nature, both of them. So it's either um, interval level of measurement or ratio level of measurement. So thus, if it's Pearson's R, we cannot use this test statistics for uh, correlations or association if our variable or our data is measured in terms of nominal or ordinal level of measurement. Remember, there were four level of measurements. We have the nominal, or ordinal, interval, and ratio level. So chi-square statistics is intended if one variable is nominal or ordinal versus another variable is numerical in nature, which is either scale or which is either um, ratio or interval level. Okay. Now, so much talking about the chi-square statistics. Let's focus our attention in the Pearson product moment correlation. Like I said, I mentioned earlier that the Pearson's R, or the Pearson's coefficient, is designed to measure whether correlation or association, association of variables exists between numerical data. But at the same time, we will also identify what's the degree of the association that exists between variable. So without further ado, let us try to describe first what are the the things that we need to learn in interpreting what is the result or the result of our Pearson's R, or the Pearson's coefficient. Okay, the correlation coefficient, the Pearson's coefficient is defined as the covariance divided by the standard deviation of the variables following the formula is used to calculate Pearson's R correlation. Okay, I'll show you or simply the correlation coefficient, or the Pearson's R, is a measure of linear strength of association between two variables. So this is actually a test or a measure of uh, the association of the variable, whether the data actually is linearly correlated or not. There are instances whether as it resembles closer to one straight line, because our target here is that this is a measure of linear correlation. So we are actually testing whether the variable actually would resemble into a straight line. Okay, knowing that it's a Pearson product moment correlation. So let's look at the situation. By the way, our Pearson's R, or R, is computed using the given formula. There are actually several formula. In fact, this book there are two, but the other book that I read or was using is, or using at the same time, is also has another formula, but I'm gonna use this one because it's more simpler, and then the variables involved is much explained clearly compared to the one that I have the other book. So we have the formula as n uh, multiplied to the summation of the product of x and y. X and y here are actually our variate, bivariate. Bivariate meaning to say it's actually paired variables. So variable x and variable y at the same time, considered as one sample size or one entry in a given sample data set. And then you have minus the summation of x and then summation of y all over. Our given divisor here is actually the square root of n times the summation of x squared minus the square of the summation of x times n times the summation of y squared minus the square of the summation of y. Okay, there you go. That is our given formula. So, and solving the Pearsons R, whatever is the result here, then we will describe whether what type of correlation exists, and then we'll interpret what kind of relationship there is if our Pearsons R happens to be this value. And then we will test later on whether such relationship as it exists, whether it's a significant kind of relationship between variables or not significant, depending on what we're going to do. Actually, we will test it using the t-test for coefficient correlation. Okay. In other words, we are going to test it using the t distribution, but this time it is computed, the t here is computed in terms of the Pearson's R or the Pearson's coefficient, which is the R. So this is our formula. By the way, our first diagram, it appears to be like this. Example, this is our situation. If we will find a data set, something like this one, you notice the data set is somehow resembles a straight line. Okay? Resembles a straight line. So take note, this value here is a bivariate, meaning to say this dot here represents one sample size corresponding to two variables, the x and the y variable. Okay? As x here representing one variable, and then y is another variable. It's a bivariate because it's a paired sample. So this is one paired sample, another paired sample. And as we put all together this paired sample that we have, and it resembles a straight line like this, then this is called actually labeled as perfect positive correlation. It's called perfect positive correlation. It's because if you notice, it resembles a straight line, as Pearson's R is a test of linear correlation. So there's a straight line that was produced as we put all together the bivariate, but at the same time, it was producing a straight line that is accessing the quadrant 1 to quadrant 3. Because you notice, if this is the Cartesian plane, I'm talking about algebraic, the Cartesian plane here. So it resembles going from quadrant 1 to quadrant 3, because if you are going to extend it further like this and like that, so the line here that was associated to our diagram would touches, or it's touching the quadrant 1 and quadrant 3, making it like having now a positive straight line, or a line that is touching the positive x-axis, sort of. And then in the case of our data set, that would appear like this. Example. So there is a linear correlation, but this time appears to be like this. This is still, there's a perfect correlation in this sense here, but this time the perfect correlation associated in our, by the way, this is called a scatter plot or scatter diagram. So simply we just plot our bivariate, all of them, and then we will look at and describe how or what type of result, or what is the pattern that is being produced as we plot the bivariate. The bivariate. So you notice it's actually resembling a straight line, but this time touching quadrant 2 to quadrant 4, and it's called, there is what we call a perfect, still a perfect correlation, perfect negative. Okay, there's a perfect negative correlation. Okay, By the way, if it is a perfect positive, then expected that R here is 1, 0, 0. Meaning to say, there is a perfect positive correlation. But if it is negative, then that is R equals negative 1.00. So there is a negative perfect correlation. And then in the event that with somehow we have it like this, okay, I'll just make it small. So you notice there is still somewhat a straight line, or there's still it's still approaching to positive, I mean straight line that touching positive quadrant. This is somehow would resemble or at least anticipate to have an R that is equivalent to positive, still positive because it's going to quadrant 1 or touching quadrant 1 and 3. That's going to be positive 8 point or rather 0.8, 0.8. Meaning to say there is actually a positive correlation going on. But we cannot say it's perfect. It's because it does not resemble a perfect or a straight line. So there is a positive correlation out of this. Okay? And then if in the event we have it like this, still there is a somehow approaching to straight line but touching the negative areas or touching the negative areas of our quadrant, we have a R equals somehow described as 0.8, negative 0.8 with a negative correlation. Negative correlation. But in that in the event that we have it like this, for example, if we have it like this, our scatter plot is actually all over surrounding and there is no certain pattern that is observed whether it is somehow resembling a straight line, whether it's positive or negative, regardless of its direction. This is an example of a zero correlation or no correlation at all, meaning to say our bivariate here are actually not related or not correlated at all. This is called, this is R equals 0, meaning to say no correlation at all, no correlation. Okay, there is no correlation happening within our variable. But in the event like we have it this way, for example, like this, if you notice, there is a pattern observed, somehow like this. There is a pattern observed. It's not scattered like this one, which implies no correlation. But this time, there is a pattern, but you notice the pattern does not resemble a straight line, whether positive or negative. So we cannot say that it's positive or negative correlation exists, nor we have a perfect positive nor negative perfect negative correlation, because there is a correlation that exists here, but it doesn't show a linearity of our distribution or of our scattered diagram. So what are we into? How do we call this one? This is called a CORV, linear correlation. Correlation. So you notice there's a curve that is being produced out of this correlation here. So sum it all, if our computed R here somehow falls on these particular instances, when a plotted, the bivariate is plotted, and then with the sample for any of this here, then somehow we have now an idea whether we have a positive, negative, perfectly positive, perfectly negative, or a curvilinear correlation or no correlation at all that exists within our variable. Okay, the variables I'm referring here is the variable x and y. So that depends upon what type of data set is x and what type of data set is y. So far, before I'll discuss to you the type of correlation, as we are going to have the ranges of R value or the R, the coefficient R, the coefficient correlation rather. Any question about this one?
Sir, sa kanang curvilinear correlation, sir, pila yung R?
Actually, there is no specific value of R here. It is just something that the R here does not actually, there is no precise value of R. This is just an illustration of telling you that if in a scatter plot, it will resemble to something like this one, but does not specifically give us what is the value of R, the range of R here. That would, if this would occur in scatter diagram form, then we have a curvilinear correlation happening. In fact, later on, I'll just discuss the ranges. By the way, R here, the R value is just, this is just an instance that is really happening, but possible. Actually, our R ranges between positive and negative 1.00. Meaning to say, if we have positive 1 or negative 1, we have positive perfect correlation and negative perfect correlation. And the rest in between are actually, it depends our specification, whether what is the range of R that is within. Now, let us look at the instance of what type of correlation there is, or how do we describe the strength. When I say the strength of our correlation or association. As association is observed or not observed at all, how do we describe it verbally when it comes to its strength? First here is we have if our R value is equal to 0.00, okay, that is our R, it implies no correlation. As explained in one of our diagram here, in our scatter diagram, so there is no correlation, thus no relationship. The no relationship here explains that variable x and variable y doesn't have any direct relationship. So they were not related at all to one another. Now, in the event that our R is equal to positive 0.01 up to positive negative 0.2. So this is 1% until 20%. Okay, that is 0.01 up to 20, 0.2. It entails there is a very low, okay, there's a very low correlation, implying a almost negligible, negligible, negligible association. So there is association going on, but almost negligible. So there is a very, very minimal association going on. As it shows that there is a correlation, but very low correlation. But if it is positive, negative 2 or 0.1 to 1 up to 0.04, this is positive, negative. So this is between 21% going to 40% of correlation. Then there is slight correlation. And we have a definite, okay, sure that relationship exists but small. Definite small relationship. That's how we describe if our Pearson's R is between 21% to 40%. Next, if we have positive and negative 0.41 to positive, negative, I'll just use the word 2, right? Can I just erase? I just have to make it more clearer so it won't appear as confusing. So we have 0.001, zero correlation. Then we have positive, negative 0.01 to positive, negative 0.2. Then you have positive, negative 0.21 to positive, negative 0.40. And you have positive 0.41 to positive, negative 0.71. 70. So we have this kind of relationship or Pearson's R value, then it entails moderate. There is moderate correlation with a substantial relationship. So moderate correlation, substantial relationship. Now, if we have positive, negative 0.71 going to positive, negative 0.90, this is now called as there is high correlation with marked relationship. Marked. relationship. Okay? Now, if you have positive, negative 0.91 R value up to positive, negative 0.99, okay, that is our R value. That is very high correlation with very dependable relationship. And lastly, when we have positive negative 1.00, we have a perfect correlation with perfect relationship. Perfect relationship. So there you go. That is how we interpret our R value. So R value is between, if R value is 0, no correlation, no relationship. If it is 0.01 until 0.2, there is a very low correlation, implying almost negligible relationship. If we have positive negative 0.21 up to positive negative zero point 0.4, there is a slight correlation, definite but small relationship. But if it is positive negative 0.41 up to positive negative zero point 0.7, there is a moderate correlation with substantial relationship. If we have positive negative 0.71 up to positive negative zero point 0.9 or 90%, that is high correlation with marked relationship. And if we have it from positive negative 0.91 up to positive negative 0.99, then there is a very high correlation, implying very dependable relationship. And then in the event that we have R value or Pearson's R to be positive or negative 1, then there is a perfect correlation with implying perfect relationship going on between the variable. But we can have it as perfect negative or perfect negative correlation, implying with a perfect or a negative perfect relationship or positive perfect relationship, something like that. So I think we discussed already the preliminaries of this one. The next thing that I would like to introduce is the test of association or the test of whether our existing correlation is significant or not. Now, this is our correlation situations. If our Pearson's R or Pearson's coefficient happens to be in this value, then this is the equivalent interpretation. Okay? But in the event that we even have it this one here, we still have to decide whether the result is significant or not. So this is now again a test of null hypothesis. So again, as we claim that relationship exists, especially as we computed our Pearson's R, the next thing that we're going to verify whether that relationship as it exists between variable, is it significant or not? Because sometimes it might be possible that the relationship occurred between variables, but it's not significant at all. It's like saying like somehow there's going on between you, but it's actually not significant. A relationship is possible or is going on, but it's actually not significant at all. Okay, so going to our test of hypothesis. Now, this is what we're going to do. Again, we will still follow our six steps of testing null hypothesis, but this time we will compute our t. Remember, we will decide, make our decision based on the critical t versus the t computed, or the t critical versus the t computed. Whichever is greater, then that's the basis of our decision. But this time, our t computed is computed in a different formula. Now, how do we compute our t? The t is computed this way. We have t equals r, and then the square root of n minus 1 divided by the square root of 1 minus r squared. Where r here is Pearson's R. Pearson's R. And then this expression here inside, this is our df. That's the degree of freedom. You notice it's minus 2. Sorry, it's minus 2. This is minus 2, implying that we're actually talking about two variables involved. So that's why no wonder our our deviation here was actually -2 for the degree of freedom. And then, yeah, there you go. And of course, R squared here is still referring to our Pearson's coefficient. Okay? By the way, this is called t-tests for correlation coefficient. Correlation coefficient. Okay? So it's called t-test for correlation coefficient because the t-test here is now used to test the correlation coefficient. So as the correlation is explained to us this way, it's being tested now whether this correlation coefficient, whether it is significant or not using t-tests. Okay? So that is what exactly we are going to do now. So first here is that we would try to identify whether correlation exists between variable. If it does exist, we would like to find out what type of correlation there is as to what type of relationship is going on between variable. And as soon as we have that result, we are now going to test also whether it's significant or not. Okay? So basically, when we test of significance, then we will follow our 6 steps of testing null hypothesis. May I have somebody to please recall to all of us what were the 6 steps in conducting a test or conducting a test of null hypothesis? As we make the statistical decision, it follows we have to do our conclusion as well. We will now
Yes.
conclude whether what will be our decision based on our statistical result. Okay, so with that saying, let's take this for example. I'm gonna write first the given. Please bear with me because if not possible, you better write the question on your end also because after writing the question in the given, I'll have to delete it again. It's because delete or rather erase it because I have only a very minimal space. So there you go. Let me write first the problem, and then after writing the problem, we will try to dissect how we're gonna approach the problem. And please do take note of what was our formula earlier for the R and for the T. Okay? As we would like to solve for the Pearson's coefficient, and at the same time, we will also know the computed T such that we can make decision whether we accept the null hypothesis or we reject the null hypothesis in our testing of the null hypothesis following the 6 steps. Okay, let's take this for our first example. Let's take this. We have here our given data set. So you notice the owner of a chain of fruit shake store would like to study the correlation between atmospheric temperature and sales during summer season. A random sample of 12 days is selected with the result given below. So you notice that we have 12 samples here, and our samples are considered as paired samples. The paired sample is represented by the atmospheric temperature and total sales. It should be total sales during summer season. Take note, the investigation was conducted during summer season. Okay? This is emphasized, it's because might be the result is different during like cold season, something like that. So, applying with this data set, we would like to find out whether there is an association exists between the atmospheric temperature and the summer sales. So it's like saying now, is it possible that during summer season, the atmospheric temperature, as the temperature gets higher, then let's say the total sale also will get higher as the relationship is both if it's positive correlation. So if it is both going up, but if the temperature goes down and also the sale will also go down, what's the relationship like that? So if it's we have a perfect positive correlation, so as temperature increases, then sale also increases. If we have negative correlation, it's if the temperature decreases, then the sale also decreases, something like that. So that is what we like to test. If we're going to look at the scatter diagram of this one and try to describe the association, I hope we can give justice to our diagram. Okay, let's say for example, this is our diagram. 75, 80, 85, 100. This is X variable, which is the temp. Take note, our temperature is in degree Fahrenheit. So you have 75 degree Fahrenheit going to 100 degree Fahrenheit. And then our Y variable, the Y axis is our total sale. Y, this is total sale. So we have, let's do it in terms of 10. That's 140, 150, 160, 170, 180, 190, 200, then we have 210, for example. So we plot 79, 147, so approximately 147, so something like here. And then 76, 143, 76, 143, so something here. Okay. And then 78, 147, 78, 147, so something here. Very near. And then 84, 168, 84, 168, so somewhere here. Then 90, 206, 206, for example, like that. Then you have 83, 55, 83, and then 55. Okay, somewhere here. Please, I cannot really show you a very precise diagram because we just approximated our grid lines. Just try to imagine we have it this way. And then you have 93, 192, 93, 192. So somewhere here. And then 94, 211, 94, 211, somewhere here. And then 97, 209, 97, 209, somewhere here. Like that. Then 85 to 187, somewhere here. And then 88, 200, 88 and 200, it is somewhere here approximately. And then 82, 150, 82, 150. Okay. Okay. So you look at the diagram. So somehow, even if it's just an approximation of our value, you notice that it is somehow producing a positive correlation, right? Positive because it's moving quadrant 1 to quadrant 3. So there is a positive correlation. So it's now saying that relationship exists between variable and it's kind of positive relationship. So we would like to solve now our Pearson's R. And then since our concern here is to test whether correlation exists between variable and whether this correlation, if it is existing, whether it is significant or not, then we will conduct our 6 steps hypothesis testing. So take note of this given because we will just tabulate this one later on. So we're good to go. We will just erase this portion here. Remember, our first step is we have to state our null hypothesis. So first, we will have our HO. In this case, our HO, R equals 0. R here represented by our Pearson's R or the Pearson's coefficient, implying equals 0. It means to say that there is no correlation going on between atmospheric temperature and the total sale of fruit shake. So in statement, this is there is no correlation between atmospheric temperature and the total sales of fruit shakes of fruit Okay, that is our null hypothesis. So in other words, we stated our null hypothesis R, the Pearson's R is just equal to zero. Meaning to say no correlation at all. Remember, when R equals zero, then there is no correlation, no um, relationship exists. And then alternative hypothesis, which is our claim, which is the claim of the owner of the chain fruit. Why would say that this is the claim of the uh, owner of the fruit shake because he's like to study the correlation. So looking at or reading between the lines, the owner of the fruit shake or the chain of fruit shake believe that there is a correlation going on. So that's what we need to test whether this relationship that the owner believe is existing and whether it's significant or not. So to prove that is that we prepared another hypothesis simply saying that there is no correlation at all, no relationship that the atmospheric temperature and the total same. But in order to make the claim of the store owner to be true, we have to reject this statement that R equals zero. So that the alternative hypothesis, which is the claim of the owner, is now then tested whether significant or not significant as relationship exists. So our alternative is R equals or not equal to zero. We are now stating a non-directional alternative hypothesis. Meaning to say, when it comes to identifying the rejection region, we do not specifically reject that there is like a positive correlation between variables, or we do not also intend to say that there is a negative correlation that exists. Okay, as R is greater than zero or R is less than zero. Because if it's greater than zero, then it's approaching to positive correlation. And then if R is less than zero, then it is approaching to the negative correlation. We do not specifically simply identify that that is so because we wanted to be conservative with the idea that in case our test here landed on either direction, we can still accommodate it with our rejection region. Simply identifying that there is no specific region um, we would like to drop our null hypothesis. We would just simply say that indeed there is a correlation going on, but we just cannot tell whether we just don't like to say whether it's positive or negative correlation. Okay? As we stated, our alternative hypothesis to be non-directional. So equivalent to this one in sentence form, we will just exactly have the statement, but of course, we will say that there is a correlation. So we will just continue that statement, the rest. Okay, I'll just put here a triple dot. We'll just continue the rest of the statement. But of course, our statement here is equivalent to this one. So we stated now our hypothesis. Step 2 is we will decide now our test statistics in our alpha. Of course, our conservative alpha as always is 0.05. Okay, that's our conservative alpha. And this time we are using a t-test for correlation coefficient, coefficient, or simply we are using Pearson product moment correlation. Okay, that is our test statistics. Step 3, we gather and collect the data. We select and collect the data. We'll not do that one because in our problem earlier, before I stated this one, I have already the data set. So assuming that the data was now selected and collected at the same time. So we have our step 4. What was our step 4? We would simply identify our rejection region. Okay? Before I'll forget, our identifying our rejection region is we need our degree of freedom. Degree of freedom. Our DF is given to us as n minus 2. No wonder that in our t-test for correlation coefficient is the square root of n minus 2. Okay, so we have actually that case. So degree of freedom is simply you have how many paired samples do we have in the problem earlier? We've got
12, sir.
okay, we've got 12 paired samples. So we've got 12 x and y samples. So we have 12 minus 2. So we have 10. And with this value, we are using two-tailed. Two. It's clear two-tailed. It's because our alternative hypothesis is actually non-directional. So we have a two-tailed test. So with this, let's identify our T critical. What is the T critical using your T distribution? Go ahead. Our degree of freedom is 10, two-tailed, and with alpha 0.05. What is the T critical?
2.228, sir.
Okay, we have, take note it's positive, negative because it's two rejection region. Since it's non-directional, so we have positive, negative 2.228. So we have our T critical. Now we intend to reject our null hypothesis on this value. So if we would illustrate our diagram, we would have it this way. Okay? Our rejection region here, both sides, is positive 2.228. Okay? And then we have negative 2.228. This is our diagram. Shaded region is reject here. I'm no longer going to use the p-value and the p-value versus the alpha. Anyway, we have already our t-critical identified as we will do the computed t, so we will just use the t-critical versus the t-computed. And then, of course, the non-shaded area here is our acceptance. Acceptance. Our acceptance region. So in the event that our T computed landed on this region, the shaded one, or somewhere here, then thus our decision will be rejecting the null hypothesis. Okay? So we have step 1, 2, 3, and 4. Step 5 is we will do the computation, correct? So, but this time, since we're doing it manually, I'm going to show you what are the things needed for the computation. Prior to, solving for y. You notice the, 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 the variables involved or the notations found in our formula for R, we've got there X. So again, we will have now step 5. So, but I'll have to erase first this portion because like I needed more space. So I'll take note of this one and take note of our null hypothesis and the alternative for the decision or the conclusion later on. So first actually is we need here, we have here the day. We have the X variable, which is the temperature, temp. And then we have the Y, which is the sale. And then we have the square of X, the square of Y, and then the product of X and Y. We just have to complete the column. What actually needed here is just the summation of all. So I'm not going to complete the exact table here. I'll just write all the entry, and then you just double check if all the entries are correct. And then you just have to understand what are these entries about. Okay, we have first is for day 1, the temperature was 79 degree Fahrenheit, and then the sale is 147. The square of 79, the square of the sale is 6,241. Where the square of y is 21,609. Then the product of x and y, 79 times 147 is 11,630. So that's exactly how we complete the table. And we complete everything going down. And then for 2, you have 76, 143, 5,776, 20,449, and 10,000. We have 28,224. Then we have 14,112. Okay, I will no longer complete the table, but anyway, this is just going on. We'll just continue this one. And then we have here the total. We'll just get the summation of this one. So, and that's the total today. So we will get the summation here, this column. For the summation of the temperature, that's equivalent to 1,029. So that's the total temperature. And then we have 2,115. Then we have 88,733. Then we have 380,887. And the summation of the product is 183,022. So to sum it up, what we need to do is we will get the summation of the temperature, the summation of variable x, the summation of variable y, the summation of the squared variable x, and then the summation of the squared variable y, and then the summation of the product of x and y variable. Because what actually needed in our formula are just the summation. So you notice there, you've got there all the summation symbol in our formula. So that's just what is needed. Okay? Anyway, any question about this one? Because I actually did not finish everything here. So please tell me if you have some clarifications or questions before I'll move further.
None so far, sir.
Okay? Anyway, you exactly know what is the table all about. You know what are the necessary squared value and then the product of the variables. So, as soon as we have this one, part of the computation for step 5, we will now move to the computation of R. Okay, wait. R is simply given to us as that n summation of xy minus the summation of x times the summation of y divided by n. Then you have the summation of x squared minus the summation of x and then square outside. Then we have n, the summation of y squared minus the summation of y, then square outside and close. So we have the formula. So we will substitute the value. Our n is 12, right? Because there were 12 paired. We have 12 bivariate. So that is 12 times the summation of xy, which is 183,222. Am I correct? Minus the summation of x and the summation of y, we have 1,029 times 2,115 divided by, okay, please forgive me, I think the space is not enough. So we have 12 times, the summation of x squared is 88,733 minus the summation of y squared, x squared. Wait, the summation of x then squared. That's 1,029 squared times the other, let me close this one first. And then the other value is n times summation of y squared, 380,887 minus 2,115 square. Okay, there you go. Let's call now what is the value of R. R equals, come on, try to solve it in your using your calculator. Oh, what is your result? What is the R? R is what? You just round up values here once. So you have to put everything in your calculator and then round up the value once. Hmm? Our value is approximately zero. It is from 0.0927, which is approximately, if we will round of the value, our Pearson's coefficient is approximately 0.93. So if you look at this one, it's positive. It's almost, if this is our Pearson's R, what type of correlation exists? 0.93. It's actually positive correlation, which is, to be precise, there is a positive, very high correlation, meaning to say there is a very dependable relationship between variable x and y, where x stands for the temperature during summer days, and then variable y is the sale during summer. Okay? We computed our R. We need to solve for our t. Can I erase this one about? Okay. Our t, the formula for t is simply R, then you have the square root of the degree of freedom divided by 1 minus r squared. So in this case, our r is positive. Take note, r here is positive, not negative. That's why I said there is positive, very high correlation, implying a very dependable relationship between variable, between atmospheric temperature and total save of the halo-halo fresh, of the fruit shake. So we have our R of 0.93. Then we have the square root of 12 minus 2 divided by 1 minus the square of 0.93 square. What is our T?
A.
What?
A.
Okay, our T is 8.00. Let's include the two decimal places. Positive or negative?
Positive.
Okay, it's positive. So we have here a t that is positive. Now, we did already our step 5, which is computing our the thetas for the thetas for correlation coefficient. So now we will move to our decision. What must be the decision if our t computed is solved this way 8.00? I erased already our r. Let's now state our decision number 6. Since, okay, since the t critical, okay, stating our alpha, and then we stated our critical value and computed uh, the computed t, comparing that one on a particular level of significance, our decision was to reject the null hypothesis. Because if we may recall, right, if we may recall our distribution, this is 2.228, while this one is negative 2.228. Since 8 here, our computed t is 8, this one, it is more likely found in this region. It is found in the shaded region, which is, if we recall, the shaded one is the rejection. Reject HO. So in other words, our T computed was found, landed in the rejection region. That's why our decision is we reject the null hypothesis. Do you follow?
Yes, sir.
So as we rejected the null hypothesis, what then is our conclusion? We will also state our conclusion. Okay? I think I'll have to erase this portion because we're good with this one. So with that saying, our conclusion, since null hypothesis, since HO was, let's just put the complete word. Since null hypothesis between the atmos summer season. There. Since null hypothesis is rejected at 5% level of significance, it implies that statistically there is a significant correlation between, statistically there is a significant correlation going on. Let me just add here just to make the sentence more meaningful. There is a significant correlation going on between the atmospheric temperature and the total sale of fruit shake during summer season. I would like to mention the fruit shake during summer season because the data gathered was during summer season. It is not guaranteed that we will end up having the same result on another season. Okay? That's why I intentionally would like to specifically mention that this result of the data was based on the summer season of data gathering.